So we have this formula, the microcanonical formula, for how the rate depends on the energy. And it leads to a lot of consequences like the microcanonical detailed balance and also the relation between the, actually this, if you believe this formula, then it leads to the Boltzmann formula just by integrating. But to actually use the formula, you have to do a lot of steps to get those numbers. We need the n, the way to do it is some clever mathematicians named Bayer and Swinehart said, you know, we have a lot of vibrations in our molecules, and we need to add up all of the different quantum states, which includes the quantum numbers for all the different vibrations, all the different rotations and translations, everything. As long as the total energy is less than E, it counts towards N of E. And so they found a very clever algorithm that looks super simple that turns out that this always gives you the correct N of expression for N by adding up over all the different quantum states. These guys were like specialists in combinatorics of how to do it. And then later, people fixed this. This was for like perfect harmonic oscillator case. You have a lot of harmonic oscillators. You can extend it to cases with anharmonicities. There's a paper by Astholz and a separate paper by Rabinovich, that Stein and Rabinovich, that show how to extend the Bayer-Swinehart. And there's textbooks about this. One of them, for example, is the Gilbert and Smith. It's a nice, clear textbook about how to do it. In reality, the J quantum number is conserved. That's the angular momentum. And so really, you should always keep track of that all the way through. So the N of E that we wrote is really like the N of EJ times the degeneracy of each angular momentum state. And the rows, you can get them sort of from Bayer-Swinehart by differences, by finite difference of the finite difference derivative. And you can get the rows analytically for the rotations as well. A lot of people want to consider, if you're trying to do such accuracy that you're going to do an experiment where you can really control the energy, then you're really interested in getting the right number. And so people want to not just make the harmonic approximation, but also include the anharmonicities. There's a paper here that shows a comparison of several different ways to do the calculations out of Barker's group. There's a thing called spectroscopic perturbation theory that gives a way to try to compute all the energy levels, including anharmonicities. You can do a Monte Carlo sampling over the different torsional conformer vibrations. There's ways to estimate how the anharmonicity, the true quantum mechanical thing, including all the internal rotations, is related to the harmonic oscillator Q. And you can also directly get it from quantum mechanics using the path integral method. And Don Trular has a paper about it. There's several papers by other people about that as well. So this is like many people know you need to do it, and several methods have been proposed, and there are softwares to do it. It's not done that often. It's kind of complicated, and when the molecules get big, it's a little bit expensive. You also have to worry about the torsion. So you have all these CC single bonds in big organic molecules. They each have an internal rotation. You need to know what the moments of inertia are of each possible internal rotation because they come into the formulas for the Qs. East and Radom have a nice paper that tells how to do that correctly. You could just do it by classical mechanics. It's not quite right, but it's not terrible, and it's relatively easy to do. Klippenstein's group does that a lot. And then there's several papers about how to try to handle the coupling between the different large amplitude motions. So you have the different rotations. So for example, this paper was studying this species. Too many things. Where's this one? Have you had keto hydroperoxide? Something like this, then you can have intermolecular hydrogen bonding between this H and this O. And so this particular conformation where it makes a ring would have the lowest enthalpy, but it would have not the maximum entropy, because if you consider the ones where they're not hydrogen bonded, then all these dihedral angles are free to do whatever they want. And so you get a lot more entropy. So this one has a high entropy, and this one has a stable or a very low enthalpy. And so at low temperatures, this one is usually the preferred conformer by a lot. But as you raise the temperature, the open ones, because they have so much more entropy, become more important. So the equilibrium between these different conformers favors the open one. This unfortunately happens right in the middle of the ignition temperature range, is where you switch from the one to the other, being the stable, the most dominant structure. And so that makes the entropy and the heat capacity curves look really weird for this one. So if you read the Sharma paper right here, it'll show you what happens and then suggest a way to try to do the calculation. But you can imagine, you can see how complicated this gets to be, because these are not flat. All of these, this carbon is like out of the plane of the other ones, because all of the CC bonds are all kind of cocked to each other. So you get quite a lot of weird geometry, 3D geometries of these big molecules. And then there's a lot of different ways that the different large amplitude motions couple to each other, and this one group in Belgium has published several papers about it. And then I mentioned the question was about if you have no barrier, what to do. And the key idea is just to do variational transition state theory. So you don't know where the dividing surface is if there's no barrier. So if there's a high barrier, the dividing surface should be like up at the top of the barrier. And that's pretty obvious. And if you try to adjust it, it'll still stay there, because that's where you get the lowest rate. But if you don't have any barrier, you have a reaction, then who knows? So for example, in this case, H plus CO, you might want to evaluate N of E here, but you could evaluate it here or here, and who knows which of these is actually the correct place, but they would all have slightly different numbers of quantum states, because the vibrational frequencies and stuff depend a little bit on the distance between the H and the CO. And so who knows which one to use. So the correct way to do it is to use the variational method, where you try lots and lots of different dividing surfaces and find which one has the smallest rate. And there's some nice papers about this by Haza, by Trular, by Miller. And then most commonly now people would use methods developed by Klippenstein to do it. There's code you can do to do it. It's expensive because there's many different possible places to draw the dividing surface, and you don't know which one is right. And so it's like you try one, you propose one as your guess, and then the computer will try to tweak it to see if it can find a dividing surface that has a lower evaluated rate, which is closer to the truth, and then tweak it again. And every time they tweak it, you have to run more quantum mechanical calculations for the V of R at the new position. So you get into, can be quite expensive to consider all the different possible places and do all the quantum calculations for each one of them. But you can do it. And today's supercomputers are fast, so it's not like completely impossible. And so there's a program called Variflex. And well, this is one probably, it's by Klippenstein. He's at Argonne. And this is the good software for doing the varying the dividing surface to do the barrierless reactions. And he's done maybe 50 cases of barrierless reactions and done all the calculations and compared with the experiment. So you can go read his papers to see a whole story about it. Tunneling. So this is how tunneling works, is that quantum mechanically, you can have a reaction even if you don't have enough energy. So you're coming in with this much energy. Classically, you would hit the wall, and you don't have enough energy to get over the wall, so you would just bounce back. But quantum mechanically, you mostly bounce back, but there's a small probability you'll leak through the wall and go through, and that's called tunneling. It's very bizarre. It turns out it's pretty important at low temperature, so below room temperature, it gets to be pretty important pretty often. So you can see that if you make an Arrhenius plot, at high temperatures, whether or not you can include tunneling just hardly matters. It's basically the same rate. But when the temperature gets low, the Arrhenius rate goes to 0 really fast because of the way the exponential dependence of temperature is. But with tunneling, it's much more gradual, and even at absolute 0, you'll still have a rate, a reaction. The most important thing to get the tunneling correction is to compute the second derivatives at the transition state correctly. And one of the frequencies will be at the saddle points. You're going up over a barrier. You find this transition state. You calculate the second derivatives in all directions. The ones out of the plane will all be positive parabolas, but this one is negative. It's going up and down, so that's why it's a saddle. The shape of this curve is really important for tunneling, and so you have to calculate that correctly. But it's not particularly hard. You just have to make sure you use a good method for the second derivatives. That there's two simple methods, a super simple method called the Wigner method, and it works, but it's perturbative. It only works when the tunneling is not important. So if the tunneling is not important, this is actually really accurate, but that's the case you don't care. When the tunneling is important, then you need to use this other method, the Eckart method, or maybe the small curvature method developed by Trular. Those ones are much more accurate, but they're more complicated. Eckart's not too bad. It's not that complicated. So there's a sort of a complicated algebra formula for it, but you can just evaluate it. Small curvature tunneling, you have to do a bunch of calculations of V of R all around the region of the transition state. And there's a software that Trular Group made called Polyrate. That's a freeware that you can get that does all these kinds of calculations for you. So it's like an automated way to do it. Here's what it looks like. You have a reaction coming in. Say A is getting closer to B. So A is attacking BC, and this direction is A getting closer and closer to B. Here's the saddle point. So you're going uphill across some contours. You get to the saddle point. This is where we would calculate the transition state for transition state theory. We would have the dividing surface something like this, a diagonal thing. So over here we would call it A plus BC. Up here we call it AB plus C. And if we were doing the way we would do the Wigner calculation or Eckart, we basically would compute the curvature along this path, this direction. That's the reaction coordinate. and then we plug it into some algebra formula and get an estimate of the tunneling. However, really, the tunneling might want to do something more like this, or somewhere in between, like that. And all those different pathways each have like a different tunneling probability, and some of them could be higher than this one. And so the things like the small curvature tunneling would consider all these different paths and try to figure out the whole sort of integral over all possible ways that they could tunnel through to get the total amount of tunneling. But to do that, it needs to know the shape of the potential in a region, not just at this point, but it has to know kind of the whole shape of the barrier. But fortunate for us, it's not that important at combustion temperatures. So if you stick to combustion, you don't need to worry about this. If you go to the rest of the world that work at low temperatures, then you really need to worry about this a lot. If you end up doing stuff in interstellar space or up in high in the stratosphere where the temperature is low, or Antarctica, then you really, really have to worry about this kind of stuff. All right, so summary rate theory. Almost all the methods start from the V of R, which was called the Born-Oppenheimer surface. Things crucially depend on the accuracy of the V of R that we calculate. So you have to worry a lot about this, particularly the barrier height. So errors in the V of R can give errors in EA, and that can give really quite huge errors. So people spend a lot of time to calculate as best possible EA you can get. If you do use good methods, you can get pretty accurate reaction barriers for most cases, and then you can actually get pretty accurate rates. We can take the classical mechanics rate theory and transform it into quantum. The exact quantum thing is too hard to solve, but the simplified one that we do as transition theory is not that hard. And you only need to compute V of R at 2 points. And if you get the V of R reasonable, you always get K of T within about an order of magnitude of the truth. And if you work really hard, maybe down to within a factor of 2. And some of the approximations that we often make are not quite good enough. So there's quite a lot of flavors of the theory that you'll see in papers. So there's like the most simplistic RRHO conventional transition state theory that's super easy to calculate, and it's even built into some quantum codes. They'll just do it for you automatically. But then, actually you have some conformers, actually you have some internal rotation, maybe there's some tunneling, and each of these things is like another thing you have to worry about. And if you have no barriers, you have to worry about the dividing surface and the variational thing, and so they can get really quite complicated to get a good rate. But typically people often would start with just the conventional thing because it's easy to do, and often it's pretty good. There's different qualitative differences between PESs. So the ones we were talking about with no barriers, a lot of them look like this, dissociations, where you have a recombination coming in. You have a different kind that have a barrier on the way out. Do you see this? So like the C6H7 one we talked about was like this, where there's a barrier between 6,6H7 and benzene plus H. That makes a big difference. So this one, there's no clear transition state, and you have to use variational theory. On the other hand, if you come in from the reverse direction, typically there's almost no T dependence, because basically you come in and you react. And these ones also often have a big pressure dependence because you need a high enough pressure to stabilize. These ones have a barrier, therefore they have a high T dependence in both directions. And this is more like the classical conventional transition state theory case. Isomerizations is also pretty important. These ones, you have 2 rate coefficients forward and reverse. They both have the same units, both per second. And we can work on those. And then you have chemically activated reactions. We haven't talked about them yet, but I'll introduce them now. Is if you come in and you have enough energy from crossing the first barrier that you're also above the barrier for the second reaction, you could have a situation where it comes in and just sails across and goes right out to make this product instead of coming in and then falling down into the well. And so you have a pressure dependence that if it's high pressure, this guy, as soon as it's formed, will get stabilized into the well, and you'll have 100% product this way. And at very low pressure, you'll come in and you'll mostly just fly across, and you'll never see any of this. All you'll see is this product over here. So this can be super confusing, and we'll talk about that maybe in the next section. All right, so that's the end of this slide deck. All right, so now we talked all about how you can calculate the thermo, how you can calculate the rates. I'm not going to talk about how to calculate the transport properties, but just believe me, it's possible. So you can calculate all these numbers. So if you make a model, you can calculate all the numbers, and then you can make predictions from the numbers. However, there's a lot of more details to go about this. All right. So, ideally, if you were doing the computations right, you'd be able to just predict things and not have to do the experiments. Even if you do have to do some experiments, it'd be nice to predict well enough that you could help guide where the experiments would be really useful. So it would really be nice if we could do this. So why do we want to do this? So one thing is, I would say that you don't really understand something until you can predict it. So there's a scientific reason to be able to predict stuff. Another one is that we really want to understand important systems. And for example, in Los Angeles, all the time, they're changing the fuel regulations because they want to make the smog go down. So that's not so easy to know what to do to a fuel regulation and what effect it would have on the actual smog that people breathe. It's like many steps, right? The fuel goes into some cars and trucks, and then eventually makes some pollution. The pollution goes up, it does a bunch of reactions in the atmosphere, eventually makes some bad stuff that we breathe. And you're trying to predict that if I make this whatever 3% change in the fuel, it's going to make some change that's going to ultimately be good for people. That's what they're trying to do. So if you really had a great computer model that could do it accurately, that would be super valuable. And also you could think the alternative, if you don't have a good model, then the government regulator is basically just, sticking a finger in the wind and just trying to guess. Oh, I think today we're going to change the fuel regulation this way. Maybe it's going to work. And you can see how this could go wrong, right? You make everybody pay extra for the special fuel, you make everybody make this new stuff, and if it actually makes the pollution worse, then that government regulator probably loses their job, right? So you really would like to have good predictions to guide this. A problem in general is that the real-world systems get really complex. There's often too many parameters in the real system to determine them all from experiments. And if you try to do it, you'll often find that your fits are ill-conditioned, which means that there's multiple solutions. And that's super annoying. After you do all that hard work with the experiments and you find out you can't actually determine the numbers you want to determine. And this even happens with hydrogen. I was surprised, but that is true. So you can't even determine the rate coefficients for hydrogen from what we can get experimentally. So you need to be able to predict most of the parameter values somehow. And then if you could do it, it's really great because you can do these preliminary assessments of all kinds of proposals to see which things actually make any sense. And in general, if you start from a reasonable model, it's much more efficient than just trying to determine everything experimentally by trial and error. Now, the need for this has been recognized forever. And so there's been a project of the chemical kinetics community for at least 100 years to try to make it possible to predict things. Historically, it was not predictive. So it was mostly postdictive. It means that after you measured something, then you knew what it did. Then you could rig up a little model that would replicate what you had just observed. But you really, if you went to a new system, you couldn't make anything until you did experiments. So you always had to wait and do the experiment first before you could make any prediction. But if you could do it the other way around, where you could predict first, then you could try to focus on experiments that would test the prediction. Because it's kind of a different way of going. And in fact, in physics, that's mostly how they go, right? That some theoretician makes some prediction and they build some big cyclotron or something, and then they go and test and see if the prediction's right, because they have a very firm prediction, and they know what to build then, right? What size cyclotron they need. They can tell you, we're going to find the Higgs boson or not. Right, we're pretty sure, because the Higgs guide made a very firm prediction. And then we have a lot of reasons that the policy people would really love to know, like what alternative fuels should we actually use. That would be really great. And also, we have to fix a lot of, currently we're using a lot of systems based on fossil fuels. We have to change them to work on something else. The more we understand what we're doing, it's going to make that whole process much more efficient, save everybody a lot of money and a lot of time. All right, now, as I said, people have been worrying about this for a long time, and a really smart guy named Dirac was worrying about this in 1929, and he went through much of what I told you in his head, and then he said, you know, I can write down all the equations, I should be able to get all the rate constants and everything, but actually I don't think I can actually solve any of the equations, because I know the theory, I know the equations, they're all completely known. The only difficulty is that the exact application of these laws leads to equations that are much too complicated to be soluble. So he just said, forget it. You're never going to solve them. Even though I wrote down the equations for you, forget it. Fortunately, the chemists didn't read the physics journals, and so they didn't know Dirac had told them it wasn't going to work, and they just kept working on it anyway. And so, 1929, Dirac says the equations are much too complicated to be soluble. But 6 years later, both transition state theory and the first quantum chemistry methods are formulated. So these guys obviously didn't listen to him. They just went ahead. And by the 1960s, the good quantum mechanical methods were formulated, also RKM. But then they were stuck. So Dirac was right. So they were stuck up to about the 1980s. They had the equations. They knew exactly what to do. They had already made good approximations. And they couldn't go any farther until, in the 1980s, the supercomputers came. And also, the numerical people invented stiff ODE solvers. So it makes it possible to solve the kinetics equations. And the Chemkin software was first written. And 1988 was a really breakthrough in quantum chemistry, that they had the first DFT functionals that were really accurate enough that they were really useful for chemistry. And so by around 1990, it was feasible to compute spectroscopy, entropies, heat capacities, all a priori pretty well. And the 1990s, quantum chemistry really took off because it was now practical. People had good enough computers and the good enough numerical methods and quantum methods that they could really get good results. In 1998, Popel and Kohn got the Nobel Prize for quantum chemistry. And then around this time also, the methods for the barrierless reactions were invented by Princeton. And so around the end of the 20th century, so that's 24 years ago, it was possible to predict the individual rate coefficients a priori, but we're limited by errors in the energies. So everything except the EA, you could compute accurately enough, but the EAs were not good enough. So it's still pretty useful. You could predict the A factors. It's pretty helpful. But then around 2010, they invented these F1-2 coupler cluster methods. And these ones actually were good enough that they give energies accurate enough to make the predictions. So let's think, we're going to make predictions. We have to have some input information. So what is it? We of course can get information from experiments. And we can also do these first principle calculations like quantum chemistry. This century, it's often easier to do the second thing than the first thing. Back in the 20th century, it was mostly to do the experiments because the quantum wasn't very good. But in both these cases, we get values for specific species and specific reactions. You get a thermochemistry for whatever you're actually measuring or whatever you're actually calculating, just that molecule. If you get the reaction rate, it's just for that specific reaction that you compute or you calculate. But very commonly, we want to predict other reactions or species that nobody's ever done any experiments on, and where we don't feel like doing the calculation because it's going to be a pain for us to do it. And so what we do is we generalize from the ones we do know, we try to make some kind of correlation to make some estimate based on an analogy for the other related reactions that we don't know about. And just overall in the chemical sciences, we're almost always short on data. And so historically, we often put all the data into the training set for our correlation, and we had like no test set. And the only way we could test is like make predictions of new systems and then do experiment to observe it. Recently, it started to change that we can start computing bigger training sets, enough data that we can separate a training set and a test set to help confirm ahead of time if the correlation's any good. So the very important thing to keep in mind with predictions from models, or any predictions, is they're never perfect. Nobody can predict everything right all the time. And in the rate predictions, often the errors and the energies are the key problem. And currently you can typically get maybe errors of order of 8 kilojoules per mole. So it's, what happens is that the ratio of this error to RT is a crucial thing. If the, here, let's see if I can write it out. So if the rate coefficient is an Arrhenius factor times EA of RT, but I don't know the true EA, that means the EA I'm using is the true EA plus some error. If that means that the calculated, my calculated rate coefficient is the true one times this factor. And so the whole thing is about, is this thing in the exponent, is it big or not? If it's much less than 1, that means that my calculation is really great. It's almost the same as the true value. But if this thing in the exponent is much bigger than 1, that means I'm e to something much bigger than 1. I'm going to have a gigantic factor error. And so one implication of this is that high temperature is easier to get accurately because at high temperature, T is higher, so I can tolerate bigger errors. But this is also why I have to spend a lot of time with the quantum chemistry to try to get better and better methods with smaller and smaller errors. And the same thing for thermo. The K equilibrium that I calculate is the true value times some error factor, which is the same shape as that. So how good are my errors? Many people, you've probably heard of this method called B3-lip. It's a very famous, yeah? There's error bars in the pre-exponential vector as well. If you have a barrier, usually the error in the barrier height is the problem, yeah. And not always. And the same for equilibria. Very often the error in the enthalpy is the main problem, but sometimes the error in the entropy is the problem. So this method, B3-lip, is super popular. DFT method is cheap. It's in all quantum programs, basically. But if you look at the errors, this is the orange ones here, the histogram of the errors, it's really big because each of these tick marks is 2 kcal. So 2, 4, 6, 8. So we have a lot of errors that are like 8 kcals per mole. That's like 30 kilojoules per mole. So that's a really gigantic error. So if you use this energies to try to get at barrier heights or equilibria, you're going to get way, way off. You can correct it some empirically, and that's what this blue thing here is, the empirically corrected method. It's better, but it's still pretty big errors. On the other hand, if you use these other methods, you can see that the error distributions in orange are much narrower. And if you use the best method down here, you can see the error distribution in orange is really narrow, and it's very unusual to have errors more than 2 kcals per mole. And if you do the corrections, some of these methods correct really well. So for example, CBS QB3 is a pretty complicated method, but affordable. And if you do the corrections, you get this beautiful bell curve distribution that's really pretty narrow. So this method is very popular for combustion calculations because it's not that expensive, and with the corrections, you get really great enthalpies. This method is so good that you don't need the corrections. And so this is good for weird things where you don't have any corrections. You don't know what the empirical corrections would be for some weird system. The problem with the corrections if you use the bond additivity corrections, you correct the reactants and you correct the products, but you're not sure how to correct the transition state because you don't know what the bonds are. Yes? Oh, yeah, thank you. Yep. So you don't know how to do the corrections for transition states because bond additivity is based on defining what the bonds are. But here we're not really sure which bonds we should count in the reaction. And this leads to an incompatibility, a discrepancy between whether you computed the rate in the forward direction, the red curve, or if you compute it in the reverse direction, the blue curve. They would give slightly different energies for the barrier, slightly different barrier heights. And so the rates would be slightly incompatible. In this case, it's about 0.5 kcal. So it's not like a gigantic error, but it's like a thing to be aware of. And it's the kind of thing that could really confuse you, because normally you think whether you write the reaction forward or reverse, it should make no difference. But because of the way we do the empirical corrections, it would actually make a small difference. There's a way to try to fix this proposed by Anantha-Raman and Milius. And so you can do that, and that would sort of help to fix the problem. Today, if you do a really good calculation, you can get rate errors with a factor of 3. So here's just some examples for these two reactions where my group experimentally measured the rates at different temperatures, and then we did the calculations, and the dashed lines are the calculations, and you can see they don't match the experiment, but it's within like a factor of 3. And so anyway, it's possible to do it. So the goal in kinetics is we're trying to predict the omega that shows up in the species conservation equations and also in the energy equation. And the omega depends on all these k's, all the rate coefficients, and some equilibrium constants. And we store everything in Chemkin format. And we have these two kinds of errors. So we have one error that the numbers are wrong. That's what I've been talking about for a couple lectures now. But there's another problem that we're missing reactions. And we call that the mechanism truncation error, that the mechanism doesn't include all the reactions it needs to have. And it's a very insidious error because once we forget about a reaction and we don't write it in our list, then we're never going to check it because we forgot about it. So whereas with the parameter errors, once you have a list of all the molecules and reactions, you can just be systematic and compute every single one or measure every single one and try to nail them all down. It's tedious. If you have 1,000 reactions, it might take you a long time, but at least it's like perfectly clear. And you can put a check mark. Check this one, I did this one, I did this, I haven't got to this one yet. But for this mechanism truncation error where you omit a reaction or omit a species, this is really bad because the model can never tell you what's missing, right? And this has to do with known unknowns and unknown unknowns, right? In parameter errors, usually we know that we don't know the number. But here, we're not even sure that there is a number that we're not even knowing, right? And implicitly, when you omit reactions, what you've done is you're implicitly assuming that the reactions have a k equals 0, that the rate coefficient is 0. K equals 0 is pretty small. That's a very small k. And so it could be really far off from what the real k is. Pictorially, the issue is that when you start to write down the species and reactions that you think are important in some situation, it's often easy to write down a few species and reactions that you're very confident. So these things in black are like species that I'm very confident are important in the pyrolysis of propene. So say I take some propene, I heat it to high temperature, it pyrolyzes. I'm really sure that all of these species are important. But I can see that these species could react to make some other stuff. So for example, the propargyl could get together and make like phenyl or benzene. And maybe that's important, but I don't know. And actually, we could also form this one over here, and maybe over here. Oh, there's so many possible reactions that could happen, and I don't know which of them are important, and how can I figure it out? And I don't want to just stick them all in, because if I do that, a bunch of these things are radicals. See, this is a radical, this is a radical. They're not going to be the final products. So if I put it in the model, I need to then add a bunch of steps for this to go to some stable product. And so then my model is going to get really big, really fast. And so this is a big problem to figure out what I need to have. So I think the best way to do it is we have to have some way to estimate the rate coefficients of these reactions around the edge, and then decide, are they so small that I think they're not going to be important? Or are they big enough that I have to put them in the model? So now I'm getting in a situation where I have to use estimates to decide even the structure of my model, like how many species are in the model or how many reactions. And another issue about this is important. What does important mean? Important is different for different situations. So if all I need to know is like what the final temperature is, if I have a fuel, if I just put CO2 and water in there and I compute the equilibrium, that's probably good enough. I'm going to get the temperature pretty well. But if I want to know the formation of N2O as a possible minor pollutant from my combustion, that's actually really complicated to get all the reactions that would contribute to the rate of formation of N2O. And so I'd have to have all kinds of intermediates and all kinds of stuff. What's my error tolerance? I'm never going to be perfect. So when can I decide, oh, forget it, I don't need it? And when do I have to put it in? So you can write down these simple things that it's true that I start with propane and oxygen, I end up with CO2 and steam. But when I try to write down the real model, it looks something like this, with all these tons and tons of elementary steps, and they all have different A factors and different EAs, and it's kind of a pain in the butt. So what would you do? So you're in this situation. You need to build a model for your system. You know from the literature some reactions in some species are probably important. You have methods, you can compute the numbers, estimate the numbers for all the species or any species you want or any reaction you want. How would you go ahead to try to figure out which reactions and species have to be in your model? And I assume for some of you this is like a real question, right? That you actually have some model you really care about. How do you know what belongs in your model? Any ideas? What would you do? Yeah?
It's just a fine idea, but you just do a sensitivity check on chemicals to realize like what really matters.
So for the ones where the model you already have, you can definitely run sensitivity. It'll tell you the ones that you already have that are important. But if you didn't write one in, it won't be in the calculation, so it won't tell you anything about those ones. So how do you decide which of the ones you haven't added yet or need to be added to your model? How could you do that?
I will start from experimental data to see.
Okay, so that's an excellent idea. Yeah, so if you could do a quick experiment and you see some product that you didn't even have in your model, that would be a big clue. Your model has a problem, and you should put that in. And then you might have to think, well, how the heck could the stuff I have in the model get to that product? So I might suggest some intermediates along the way. So that's a really excellent way to do it. Yeah.
Yeah, so you start with the simplest 2-step or 3-step mechanism. Plot flame speeds because that is what you need to describe flame thickness and things like where will the flame stabilize and stuff like that. And see how close it gets to experiments because these have been done with experiments as well. Then if you don't get it close, you can do all this with Cantera quite easily. Then add another reaction and see how close you get, and then keep building.
So let me see if I'll restate what you just said. Is you start from some super simple thing, simple model. You compare it to your experiment. If you're not happy because the agreement's not good enough, you say, boy, I need to improve, so I need to add something else. So then I think of some other reaction or some other species and just stick it in my model and try to go ahead with that one, and then I recompute and compare with the experiment again. And I can keep going on and on like this. And I think the idea that you would iteratively add stuff in to make your model more complete and then kind of do some kind of check to see if you've actually made any improvement. That would be a really smart idea. I think that's a really basic concept, that we're going to try to iteratively extend the model, improve the model, make the model more complete somehow. Yeah. But exactly how to do it might not be so clear. Is that okay? As a summary statement, yeah. All right. Yeah. So if we're working in fuels in like the gasoline range, we might typically have something like 1,000 important molecules, maybe 10,000 important reactions. But there's a lot more possible species and reactions that might be important, but we're not sure. This is now getting to the range where we just don't want to do it because it's too much work for a human to handle a list of 10,000 reactions. And if you try to do it, you'll make mistakes unless you're really, really systematic. Because it's like, it's a book, right? 10,000 reactions. Just to write them all down, you can write down, 50 on a page. And so it's like 10,000 reactions, like a 200-page book of reactions, right? So most students these days are not that good at reading books, so probably by the time you get to page 98, your memory is completely gone. You can't remember. Did I see that reaction already before? I can't remember, right? Okay. I'm old, so I'll stop at page 57. Get too sleepy. I can't be able to keep going. So we really need the computer to help us with this. And for sure, if we need good numbers, we're going to do quantum chemistry calculations, but that's going to mean that we need a supercomputer. So now we're going to do a lot of computations. And then we need good estimates to try to figure out which things are important or not. So this goes back to this picture. If we could estimate which of these things are negligible, we could just erase them, and that would save us a lot of time. So if we had some way to make estimates that were reliable enough that we would trust them, then we might be able to avoid dealing with a lot of things. And experiments, when you get to these giant models, experiments are really not that useful anymore. So when you start with a little tiny model, then the experiment could even determine the parameters of the model if it fits. But once you get to models that are a scale of 1,000 species, it's like there's too many parameters in the model. You could make by tweaking the parameters, you can make anything fit anything, right? And so now it's not really that useful as a way to go. So you're really going to need a lot of calculations. And then, of course, you have to accept that all these numbers are going to have uncertainty. So you really have to do what's called UQ, uncertainty quantification, to try to figure out what's the uncertainty in the predictions from these kinds of models. This is a result from a paper from 2009 of the sizes of models. You can see that even back then, there were many models were getting up to 10,000 reactions and over 1,000 species. And since then, this is way up here. There's so many models that are much larger than these now. So what we would like to do is have the computer build the model for us, as well as doing solving the simulations for us. So actually write down all the reactions, write down all the species, compute all the numbers, and then make the predictions for us. This is kind of complicated goal. So let's start with a simpler case. We have to figure out what are the important reactions in species, but we don't want to include unimportant species and reactions because it's just going to clutter up our model with a bunch of stuff that doesn't matter. It's going to make the computations much longer and harder for us to see what's important if we add extra stuff that's not important. And then we need to compute all these numbers accurately enough. And we can use a mix of estimations like from functional group estimates or by quantum chemistry. And then we have to do everything numerically automated. So once we get these giant models, it's really not practical for humans to do anything with them. So you need computer tools to help you to do everything. And there's a lot of people who have worked in this field. So this volume of comprehensive chemical kinetics is just about this topic. Also, this volume of advances chemical engineering. And basically, this is a 100-year project. And the project for automating the kinetics is it maybe last 50 years. So this is like many, many people worked on this for a long time. We have commercial software, things like Chemkin or Cantera, that if you have the list of all the reactions and all the parameters, they can just solve it for a bunch of simple geometries and give you the predictions just fine. So this is like well established since like, I don't know, 1985 or something. The challenge is this input. How do we make this list of all these reactions and rate parameters and make sure we didn't omit any species that are important? So we need a way to represent the species on the computer that's unambiguous. We need to be able to construct the reactions between all the species. We need to estimate all the numbers. And we need to have some kind of metric to decide which species and reaction belongs inside the model. So we have a model that's like our current model. And then we see, well, you know, that these species can actually make some other products, say these two. And we have to decide, do we want to include these products in the model or not? Are these negligible or are these important? And then there's a bunch of other stuff that could potentially be made eventually, but can't be made in a single reaction step from these guys. So we might have to worry about these later, but let's not worry about them right away. Let's just worry about the ones that we can make in the first generation. So you have several options. So historically, what a lot of people have done is just human selection. So human expert just goes ahead and just says, I think these guys are important, I'll put them in. And if the person's really an expert, this could be a really smart way to do it. Another way is just to do it by generational growth. They say, well, if it takes 4 reaction steps to get from here to here, that's too many. It's not important, so I won't worry about these guys. So that's another idea. That actually works in some situations where the reactions are like really slow and only run to low conversion. Another one is directed growth. So you say, well, I know that this type of species always tends to fall apart this way. So the moment I put the species in, I'm immediately going to add that whole pathway of how it's going to decompose because I expect that's going to happen. Because that happened for other molecules that were similar to this one. And this approach, there's some programs that like XGAS, they do this approach automatically for you. So they have for certain classes of molecules at certain conditions, they just know, oh, very commonly this will immediately lead to these other guys, so let's just stick them all inside. And then you can do a kind of brute force numerical method where you say, well, let's just list all the possibilities and numerically evaluate each one and decide which one's the fastest. And that's the one that's important. So in the RMG world, we take this existing stuff that we have in like Chemkin or Cantera, and we wrote a software to try to create this list called the reaction mechanism generator. And this is based on a documentation of assumptions of how molecules react and also the estimates of the numbers. But these things, if you do it, well, so you can go ahead and you can run RMG forwards where you take the database, use it to add more reactions to your existing model, and it'll make an even longer list of reactions. And then you can make a prediction. The interesting thing then is to do sensitivity analysis on this prediction to see which numbers in this model matter. And the ones that matter, go back and do quantum calculations on those to try to make them more accurate, and then store them to use them later to make better estimates about what really matters and what reacts. So the software reaction mechanism generator, which I didn't mention, but this one is based on this last method, this brute force checking. The way it does is it uses elementary reactions, it estimates all the numbers, and it's open source. And so you guys can use it if you want, and you can change it if you want. It's available at this source. And how it works is you have to provide the conditions you care about, the composition and temperature and pressure, and also you give it the libraries of all of the information it knows about. We have a bunch of libraries available. You have to specify error tolerances, and then it'll automatically generate a kinetic model in these formats. And so back to the case I showed you, you had a model, it could make 2 different products. The computer decides that this product is more important, so it sticks this one into the model. And now we have a new version of the model. And then we can reassess again to see where we are. This is the loop of what it's doing. This is maybe details. Well, a key thing is you have to figure out what's possible, what reactions are possible. And there's a lot of reactions in the world. And so what RMG has is about 55 different reaction families these are what's considered to be possible. And here are 8 of them, I think. Or sorry, 7. I don't have many here, 7. So these are like, H abstractions, intramolecular H abstractions, additions, recombinations, migrations, some disproportionations. So these are like some common families that show up in combustion models and that are in RMG, and there's a whole bunch more. But if we don't include the reaction type, the computer won't know it exists and won't know it's possible. So that's the challenge. I think, well, each reaction type, you have to write down a little recipe of which bonds are breaking, which bonds are making. And then you have to have estimates. So I think I'll stop here, and we'll pick up here tomorrow. Thank you for your continued attention.